So welcome to the second half of these notes where we're going to talk about, well, what happens if an object is not at equilibrium? So to be in equilibrium means that all the forces balance, right? Whatever my horizontal forces are, they balance. Whatever the vertical forces are, they balance. Then we're in equilibrium. So if we're not at equilibrium, so we have some unbalanced forces. And so this means that the object is not going to stay at rest, or it's not going to continue moving at a constant speed. So that means then that the object must accelerate, right? So forces, unbalanced forces, cause accelerations. That's really important to understand that. An unbalanced force will cause an acceleration. So first of all, let's look at Newton's second law, right? The acceleration of an object is directly proportional to the net force and inversely proportional to the mass. So what does that mean? If acceleration, and this just means proportional to, if acceleration is proportional to the net force, that means if I double the net force, I get double the acceleration. And that should make sense, right? If I push on an object twice as hard, it's going to accelerate twice as fast. But it's also inversely proportional to the mass. So what that means is if I double the mass, I'm only going to get half of the acceleration. Okay, so that's what that means. If I double the mass, I get half the acceleration. If I triple the mass, I'll only get a third of the acceleration. Now, if we put those two statements together, we get Newton's second law. So this is Newton's second law. Acceleration equals net force divided by mass. And net force just means we add up all those forces and we end up with something that's unbalanced divided by the mass. And you'll commonly see that this way as F net equals ma. It's written this way on your formula chart, A equals F over m, but F equals ma is a pretty common way to see that. And so the net force we're talking about here is just the sum of all the individual forces. Now, remember, force is a vector. Force is a vector quantity, so it has x and y components, it has direction. So whenever we write these equations for Newton's second law, we're going to need to be real specific. We're going to have to write an equation for the x direction, we're going to have to write an equation for the y direction. So some tips for solving some of these problems. So always draw a free body diagram. Then resolve those vectors into components. That just means draw their x and y components. Write equations of motion by adding and subtracting vectors to the net force. Always write the larger force first minus the smaller force. You'll see an example where we do that in a second. And then solve for any unknowns. So let's look at that box again, right? So I had that same 10 kilogram box being pulled across the table to the right with a rope and an applied force of 50 newtons. Calculate the acceleration on the box if there's 12 newtons of frictional force. So remember, before when we pulled at 50 newtons, if we were pulling it at a constant speed, we had to have 50 newtons of frictional force to cancel it, to balance those forces out. Well, now we have unbalanced forces, right? I've got 50 newtons to the right. I'm only going to have 12 newtons to the left. So the result is going to be that this box will accelerate. First thing I do is I label all my forces. I know I have mg going down. I know I have the normal force going up. I have the applied force of 50 newtons to the right, and I have the frictional force to the left. Now, we're concerned with the acceleration of the box. Well, the box is not going to accelerate up or down, right? I'm pulling it to the right. So the only forces I need to look at are the ones in the x direction, right? I don't need to worry about the vertical forces because the vertical forces are not going to cause it to accelerate horizontally. So looking at Newton's second law for the horizontal forces, the net force equals ma. There we go. That's where I'm going to start. Well, the net force is the applied force minus the frictional force. Remember, I'm only looking in the horizontal direction. So to the right, I've got the applied. To the left, I've got the frictional force. And that has to equal ma. Then I can plug in my numbers, right? I know the applied force is 50 newtons. I know the frictional force is 12 newtons. And I know the mass was 10. From there, I solve for a, and I find out that the acceleration is going to be 3.8 meters per second squared. Okay, here's that same example from before also, right? So this is the two objects tied together with a rope going over a pulley. So I'm told mass 1 is 3 kilograms, and that's the one that's resting on the table. I'm also told the table is frictionless, right? So I don't need to worry about the frictional force on the table, but it's sitting on the table, that's 3 kilograms, and it's attached by a rope to a hanging mass of 11 kilograms. And I'm asked to find the acceleration of each mass and the tension in the cable. Okay, so first thing I need to do is draw my free body diagrams. So I have m1g over here and I have m2g over here. It has to be m1 and m2 because my masses are different. Now I've got the normal force going up and I have tensional forces on both objects. And those tensions are the same. So here's what I need to do. I'm going to look at the direction of motion, right? So when I'm looking in the direction of motion, this object would be pulled downward, right? It's going to be pulled downward. What forces do I have in this direction? Well, I've got m2g down minus the tension because the tension's going up. And those forces are the only two forces acting on object 2. So net force equals ma. And I'm just writing that for this object. Well, what about on this object? What about on mass 1? Well, on mass 1, in the direction of motion, the only force I have is the tension. So the tension is the net force on this object. So tension equals m1a. Now, from here, I'm looking to solve for the acceleration, right? This is the acceleration of object 1. This is the acceleration of, this is the acceleration of object 2. This is the acceleration of object 1. But those accelerations are going to be the same, right? Think about it. If I have two things that are tied together and they're being pulled together, if one object is accelerating, the other one must be accelerating at the same rate. So those a's are going to be the same. So somehow here I need to solve for a. Well, I know m1 and m2. That was given in the problem. Tension I do not know, right? Tension's an unknown, so I need to get rid of it. Well, I know tension equals m1a, so I'm just going to take this m1a and I'm going to plug it in for the tension up here. I'm going to substitute. Tension equals m1a, so it's going to go in right there. So when I do that, I get m2g minus m1a equals m2a. Rearrange it a little bit. I'm going to move this term, this minus m1a, I'm going to move it to the other side. I want to get all the terms that have an a on the same side. So I just add it over to the other side. Now I have two terms over here that both have an a in common. So I'm going to factor that a out. Right, I pull the a outside, and that leaves me m2 plus m1. Think about factoring as being like the distributive property, but in reverse. Right, so I'm going to pull that a out of both of them. Then I need to get the a by itself. Well, how am I going to do that? Well, I'm going to divide by m1 plus m2. So that puts it down on bottom over here. So the acceleration is going to be m2g from here divided by m1 plus m2. That came from right here. All right, and notice this looks a lot like Newton's second law, right? Acceleration equals the net force divided by the mass, divided by the amount of inertia, the resistance to the change. All right, the net force on this object is coming from gravity, right? Gravity is what's pulling this object down. That's what's going to cause this object to move to the right. So that's the total force, right, is the weight coming from m2. And the total inertia of the system, the total mass, is the mass 1 plus mass 2. And so I just plug in my numbers, and I wind up getting 7.7 meters per second squared. Notice that's less than 9.8. This object's not in free fall, right? It has a rope that's providing some resistance that's not allowing it to fall in free fall. So a couple of other things real quick. So you were also asked to find the tension in the cable, right? So we found the acceleration. Now I need the tension. Well, tension was just m1a. So I'm just going to plug that in, right? Tension was m1a. I know m1 was 3. I found the a just a second ago. That was 7.7 meters per second squared. I find the tension in the rope to be 21.3 newtons. Now, you may be asked to do this on a lab, so I just want to point this out for a second, but we could actually figure out the mass of an object based on the force we applied and the amount of acceleration it experiences, right? So if I plot force versus acceleration, I should get a straight line, right? Because these two things are directly proportional to each other. I should get a straight line whose slope is equal to the mass. So that would be one way to figure out the mass of an object if you didn't have, like, let's say maybe a scale. Okay, I hope that helps. Let me know if you have any questions.